Hello. This unit is going to be on trainability. Central dogma, or at least something that's very frequently said, is that deep networks are powerful because they're expressive and they're trainable. And it's clear that they are very expressive. If you could set the parameters by hand, you can make them do almost anything. However, trainability is a much trickier issue. Historically, it's been true that people get frustrated by being unable to replicate results in deep learning, and often that has to do with replicating the training, the stochastic gradient descent. So in this unit, we're going to talk about recent progress that's been made in making the networks much more trainable. Since the deep revolution, there's been a lot of progress in making the networks trainable. The main issue in training deep networks is maintaining meaningful gradients. So remember that the main tool used in training networks is stochastic gradient descent. And when you're doing stochastic gradient descent, you're updating the parameters based on the gradient of the loss function with respect to the parameters. The problem is that the gradients, when you do backpropagation through a network, the gradients can fail to be meaningful. And there's two problems, often called vanishing gradients and exploding gradients. So we're going to talk about what they are and what's been done to make these things more tractable, less of a problem. So remember that the fundamental unit of deep networks is the linear threshold unit. So we add up a linear sum, we compare it to a threshold, and we pass it through an activation function, a kind of threshold function. And the standard one is the sigmoid function, which continuously, smoothly goes from 0 to 1 as you pass through its active region. So it's continuous and differentiable, therefore it has gradients, therefore stochastic gradient descent is meaningful on it. But you notice that if it's too far below the active region or too far above the active region, the gradients are 0. This red line is just the derivative of the activation function. So if those gradients become 0, then the gradient isn't giving you any real meaningful information. It's not making the SGD do appropriate updates. So this is a source of vanishing gradients. Now, at the dawn of the deep revolution, the AlexNet in 2012, one of the innovations of AlexNet was to replace the sigmoid functions with rectified linear units, ReLUs. And the ReLUs can also be thought of as a kind of linear threshold unit, except when it's 0 up to its activation point, and then it's just linear forever. So it never saturates. So once it's active, you've always got a gradient, no matter how far up this goes. And the replacement of the sigmoid function with the ReLU really improved the trainability and made a significant difference in AlexNet. Okay, there's another source of problem with the gradients, and that is if you have a deep network, like suppose I have many layers of convolution in a convolutional network. We've seen that modern networks can have 50, 100, maybe even 200 layers. Each layer is multiplying the weight, the signal, the data terms by weights at that layer. So you're multiplying the data, your tensors, your data, by weights every time you go up a layer. And if those weights are too large, it means your values are headed for infinity. And if those weights are too small, it means your values are headed for 0. So it's very important to have those weights be just right? Not too large, not too small. You'll get either vanishing gradients or exploding gradients. So there's been progress in understanding this problem and doing careful initialization. So we want to initialize the weights such that they're just right, such that the data as you're going through the network stays in the active region of the activation functions, of these threshold functions. So in particular, what we're going to do is try to initialize the weights of the network such that we expect that every linear threshold unit, as it gets passed over various data, is seeing inputs to the threshold function, to the activation function, is seeing inputs to the activation function that have zero mean and unit variance over the distribution of inputs that are given to that activation function. So there's something called Javier initialization. This is, I believe, since the deep revolution. So we're considering here a linear threshold unit. So Yj for some neuron J is an activation function applied to this matrix vector product and compared to this threshold for J. Now what we would like to do is that this value, that the value that comes out, what we really want is that the value that comes out of this expression has zero mean and unit variance. So it's in the active region of this activation function. We want the input to the activation function to have zero mean and unit variance. And we're going to initialize in Javier initialization, we're going to initialize these bias terms to be zero. So what we really want is that this quantity, right? So this quantity is what's being fed to the J activation function. We want this quantity to have zero mean and unit variance. So what we do is we initialize the weights in this weight matrix to have zero mean and to have a very specific variance. And the variance is set to be minus the square root of 3 over the size of the sum that's being taken. So as I add up more terms, the variance gets larger. And it gets larger in proportion to the square root of the number of terms I add. So if I initialize each weight to be in an interval that's the square root of the number of, it's 1 over the square root of the number of terms I'm adding, that means that when I add that all together, it's going to have zero mean and unit variance, assuming that these variables, the input variables, have zero mean and unit variance. So this preserves as a kind of invariant the idea that the values, the data values, have zero mean and unit variance. So you can, it's a simple little calculation you can do to show that if it's initialized, I may have said Gaussian, we initialize it to be a uniform distribution in this interval. And it's a simple calculation that if you initialize it to be a uniform distribution in this interval and you assume that X is zero mean and unit variance, then this product is zero mean and unit variance, assuming these are independent, assuming X is independent of the weights. Okay, so this idea that things should be in the active region of your activation function can be addressed in another way called batch normalization. So this is run during training. It's no longer an initialization phenomenon. It's run during training. And during training, what we're going to do is we're going to, in some sense, measure the mean and variance coming into a linear threshold unit. And we're going to subtract the mean and divide by the variance. Okay, so if we do that, then we've measured what's naturally coming in and we've converted it into zero mean and unit variance. So this is the way it works. So we're given some tensor. This is the batch index. Eventually I'm going to stop using the batch index, but we're still using the batch index. So we've got a batch index and a neuron index. This is a simple case where we're just worried about one neuron index. So this is the neuron J. And we've got values that are coming into the neuron J. And what we're going to do is measure the mean and variance of the values coming into the neuron J. And so we're going to compute a mean over the batch. Okay, so remember we're running with these batches. So in a batch, I've got a bunch of different examples of this neuron. And I can compute the average over the batch of what's coming into that neuron. And that's a mean for this input. I can measure the variance. Once I've got the mean, I can take each point in the batch and subtract the mean and square it to give me a variance. And then I take the square root of that and I divide by 1 over b minus 1 because there's b minus 1 degrees of freedom here. And this is an unbiased estimate. If you've taken statistics, you've seen that. So then I can take the input, this input, which may not have zero mean and unit variance, and I can simply convert it to a value that should by subtracting the mean and dividing by the standard deviation. Now, this mean and standard deviation are a property of the batch, right? So I need I need statistics to calculate the mean and variation. When I go to calculate this when I go to make this adjustment at test time, I simply use some fixed estimate of the mean and variance. At test time, you typically think of fewer points. You don't have batches, the same size batches, or you don't have batches at test time. So at test time, you just fix these parameters. You don't compute them from the data. So in batch normalization is most effective in convolutional neural networks. I've got a slide on that in a moment. But in convolutional neural networks, remember that there's a weight tensor that's being used at every position, and it's the same weight tensor being used at every position. Sometimes the weight tensor is called the kernel, and you're convolving the kernel with the image. Now that weight tensor, since it's the same at every position, in some sense, if you've got a given output neuron of the convolution, I'm going to look at a fixed output neuron of the convolution, that same neuron, the same system of weights, is being used all over the image. So instead of just doing a batch statistics at one place in the image, you do batch statistics for that neuron index over the whole image. So what that means is you calculate a mean by summing over the batch. You do sum over the batch, but you also sum over the XY coordinates. So you sum over the batch and the XY coordinates of the tensor of this neuron's tensor, right? So this J is really naming a neuron, and it's the same weights that are being used everywhere across X and Y. So we get a batch and spatial mean for the neuron J. And we get a batch and spatial measure of the variance. So we get a batch and spatial standard deviation, and then we do the correction based on the batch mean and standard deviation. We do a spatial averaging. Sometimes it's related to what's called layer normalization. So you're normalizing this particular unit across both spatial and batch dimensions. Okay, and the batch, when you go to PyTorch and look up the batch layer, in addition to doing what I just said, before it feeds it to the activation unit, to the activation function, it does an arbitrary affine transformation. It takes the thing we just defined. So this is what we just defined, which is corrected to have zero mean and unit variance. And it takes that and applies a scaling and an offset. And this makes it possible for the system to learn, could even learn to undo that normalization. It makes it possible for the system to express different kinds of inputs to the activation function that aren't necessarily zero mean and unit variance. And this has been found to improve the batch normalization somewhat, I think, but it's still true that the main thing that's going on is controlling the values to be in the active region of the activation function. Oh, I should also say that an affine transformation like this has a significant effect on SGD. And exactly, the effect that this has not been, in my opinion, really understood or experimented with adequately. So batch normalization is widely used in convolutional neural networks. It's been quite successful in convolutional neural networks. We're going to talk about recurrent neural networks that are used in language later, and batch normalization has not appeared to be very useful there. So it does seem specific to the vision architectures. And it's also, as I said, the point is to get it to get the value in the active region of the activation function. So it's typically used just prior to an activation function. The activation function is not part of the batch normalization. The batch normalization just does an adjustment before you feed it to the activation function. The original paper on batch normalization talked about this thing called, motivated it in terms of internal covariate shift. And there was a well-known talk at NeurIPS that was complaining about the lack of understanding in the lack of theoretical framework and understanding in deep learning. And the speaker said, "What is internal covariate shift?" And the audience broke up laughing. But let me try to explain the intention of that phrase, internal covariate shift. So if you're training a linear regression and you train it on one data set, and then you try to use it in a different data set, the inputs to the neural network are called the covariates, and you're shifting the covariates to a different distribution. So that's covariate shift, and you want your network to be effective. You want your linear regression, your linear predictor, to be effective when the distribution of the input changes minorly. And it was found that if you do this normalization on the input, so that the input stays zero mean and unit variance, if you sort of whiten the input and train your linear predictor on whitened input, then when the input distribution changes, you can at least make it zero mean and unit variance, and that sort of that reduces the change in the covariates and makes your network more effective on a different distribution. So that's covariate shift. Now, if you think of a neural network as having many layers, and all the layers are being trained, so the input to one layer is continuously shifting as the layers below it change. Now, you'd like that layer to be, to be doing something useful and learning something useful, even as the layers under it change. So that's internal covariate shift. The idea that the layers beneath you are changing, but by compensating, by making the signal that's coming in zero mean and unit variance, you're making yourself less sensitive to the change in the input that's happening as you're learning. Very, very hand-wavy. But hand-wavy arguments can work. Okay. This is one of the big developments, in my opinion. It's been a while now, but this is 2015 was the introduction of residual connections. So we want to make the gradients meaningful. We want to keep meaningful gradients. So instead of just layering the convolutions, as was done until 2015, what we're going to do is we're going to make the layers sort of side computations. So we're going to go, these are convolution layers coming down in this picture. So the input's at the top, and we're running a convolutional neural network, say, down this network. This is the convolution. So it runs a convolution on the image to get a new, on a tensor that's here to get a new tensor. But then instead of passing that tensor to the next convolution, you add that tensor to the input. So you add this modification to this. And you can think of this thing as trying to fit this network to a good difference between what's coming in here and what's wanted here, right? And the difference between what you're actually predicting and what you want to predict is often called the residual. So the difference between what a linear predictor predicts and the actual data point, if those are numbers, the difference between the prediction and the true value is called the residual. So you're trying to fit this to the residual between what's coming in here and what this network wants. Just trying to explain the terminology. The important point is that if you look at the gradient of the loss, which is happening here, the data tensor that's coming out here now is a big sum, right? It's a sum of all of these side computations. And that means that the gradient of this data tensor with respect to that first layer is as if these, or is at least as strong as if these things did not exist, right? Because that first term is added directly into the output tensor. So the gradients go right back through these sums. Right, you know, this does not disturb the gradient path that's going back through the sums. So this is really sort of directly addressing the meaningful gradient issue. Everything is in some sense directly connected to the loss functions. The loss functions training everything down that additive path. Sometimes Schmidt-Huber introduced a similar concept, and he called this the highway path, and these the detours. Residual connections have completely taken over. All the modern architectures are full of residual connections in transformers and everywhere. Okay, so this is just doing it in an equation, in a formula. So here's a simple convolution residual connection. So I'm defining the next layer to be the result of a convolution on the previous layer. And then I'm going to take the convolution on the previous layer and add in the previous layer to get the next layer. And remember, I've got this convention where if I use capital letters, I'm referring to the whole tensor. So, and this code would work perfectly well in NumPy, in edF, right? In edF, we would write a convolution procedure that would take the weight matrix, the bias terms, the thresholds, and the previous layer, and this procedure would apply that, apply the convolution formulas to get an output of the convolution, and then you take that tensor and add it to this. Now in ResNet, the original 2015 ResNet, and this is something that is also common, they'll do two convolutions before they do the addition. So we've got an input tensor, we do one convolution to get a next tensor, then we take that, we do another convolution to get yet another tensor, and then we'll take the original input and the output of the second convolution and add those together to get the next layer. Right, so we're still adding in things, but we only add in every two convolutions. So here's a picture of ResNet. Here's an input, and there's an initial convolution layer, and then we have these two convolutions, and then we take two convolutions, and then we take the input and add it to the output of those two convolutions. Two convolutions, take this input, add it to the output of those two convolutions, and so on. It's shifting colors here. Remember that a classification network will reduce spatial dimension as you're going through the convolutional network, as you're going through the CNN, the convolutional neural network. So a change in color here is when spatial resolution has been reduced. So let's talk about that, reducing spatial resolution. So in what I just showed you up here, all of these tensors, all of the tensors being passed here before we reduce the spatial resolution have the same shape. So this equation I showed you before, in this equation, everything has the same shape. All of these tensors have the same spatial dimension and the same number of neurons at each spatial position. But what if we do, so the modern way of reducing the spatial dimension is to do a strided convolution. So we only compute a value every second position in the input tensor. So we get a smaller spatial dimension. So the stride is how far we move per linear unit. So if the stride is 2, we're moving we're calculating a value every other position in both X and Y of the input tensor. So the spatial dimension, for stride 2, the spatial dimension goes down by a factor of 2. So suddenly, this layer has half the spatial dimension that the input layer had, because it's a convolution stride S. Or whatever. Suppose S is 2. If S is 2, this is half the spatial dimension. And then this is half the spatial dimension. And then the equation I had before wants me to add L1, which had different spatial dimension, to this layer, which has different spatial dimensions. So what we do is we take the input layer and we adjust it to match the spatial dimension that we just created by the stride. So another point to make is typically when you reduce the spatial dimension, you increase the number of neurons per position. So the spatial dimension is getting smaller, the number of neurons per position is getting bigger, and you try to keep the amount of work sort of constant as you're going deeper in the network. So the spatial dimensions have been reduced and the number of neurons at the layer has been increased. Okay, and this is just the formula that was used in the original ResNet paper. This is this is taking the layer L and adjusting it to have the right shape. So we're just downsampling it by taking these coordinates and multiplying them by S to see where to look in the input. And we also pad by 0 for the extra neurons. So a neuron, this is going to have more neurons to get this shape. We just initialize the extra neurons to be 0 and keep the old neurons that are there. So we adjust the input to be the same shape. So let's go back and look at this. So 2 convolutions, we take the input add. This convolution reduces the spatial dimension. It changes the shape. We do 2 convolutions at the new dimensions, and then we add an adjustment, a shape adjusted version of the input around here. So the shape adjustment is this dotted line. And we do that several times. We adjust shape several times. Now so this is ResNet 32. People typically use like a ResNet 50 or ResNet 100, number of layers, 50 or 100. When the original paper came in, he went to the much deeper networks. They introduced bottleneck layers. So the idea behind a bottleneck layer is you're going to do 3 convolutions instead of 2. You do 3 convolutions and then you do the addition. That tilde shouldn't be there. I'm not going to worry about changing. This equation is going to all be the same shape. So what happens here is the first convolution is going to go to a much smaller number of neurons. So you're going to take, there's some number of neurons being used at the input layer, typically a fairly large number of neurons. In a bottleneck layer, you put that through a convolution that reduces the number of neurons. Remember that the weight matrix used in the convolution is defining the neurons at each spatial location, and there is no the number of neurons at a given spatial location can be larger or smaller than the number of neurons at a spatial location in the input. Those are just 2 different indices, which can have 2 different dimensions in the weight tensor. So we can do a convolution that reduces the number of neurons. And then we do a convolution that keeps the smaller number of neurons, and you do a convolution from the smaller number of neurons to the smaller number of neurons, and then you do a convolution that boosts that back up to the larger number of neurons that you had at the input. So at this point, this layer, little l plus 3, has the same shape as the input layer because the input layer wasn't reduced yet. So this is a bottleneck layer. You reduce the number of units, do a convolution, grow it back, so it's a bottleneck, like an hourglass, and then you do a residual connection. You add the input to the layer you got from the bottleneck. That tilde should not be there because these are now the same shape. And the big point of the bottleneck layer is that the size of the weight matrix is very sensitive to the number of neurons. The size of sorry, there should be no batch index in the tensor. That's in the weight tensor. That's bad. The weight tensor has size sorry, this should be delta x, delta y. The point is it's got 2 parameters for the neurons, and the size of that weight tensor is proportional with the product of the 2 sizes of the number of neurons, the 2 j's. So if you can make one of these smaller, it greatly reduces the size of this weight tensor and greatly reduces the time it takes to the amount of computation you're doing in these things. So all of these layers have at least one index that's smaller, and this middle layer, both indices are smaller. So there's this general notion of a residual connection, right? So for a residual connection, we're gonna take some input x, compute some tensor from x, and then we're gonna add that to either x or some shape-adjusted version of x to make this addition work, and then we get our new layer. So the point is that the new layer, the new tensor, this new value, if you take the gradient of this value, it's going straight back to the input as well as going back to R, and that's really the point of the residual connection. And another big sort of thing people like, a sort of compelling point about ResNet is its simplicity, right? It tends to be true that simple architectures are expressive and trainable, and you find the right set of simple ideas to build these architectures, and simple things are expressive and trainable. So you want to compare ResNet to this inception network, and you can see that conceptually this thing is going to, well, empirically this thing works at least as well as this, but it's much easier to think about. It's worth pointing out that ResNet is my favorite example of this idea that deep networks are expressive and trainable and therefore can do anything. So ResNet, significantly, I don't know about dramatically, really significantly improved image classification. ResNet is used in protein folding. I don't have time, I don't want to go into that now, but it's a central tool in protein folding. ResNet is the network used in AlphaZero. So this same architecture can do vision, can do protein folding, can do chess and Go and shogi. So it's providing a pretty clear body of evidence that it is true that there are universal architectures that can be trained, that are effective at a wide variety of problems. So it supports this kind of idealistic vision that you just have to find the right universal learning architecture. Okay, see you next time. Thanks.